welcome to our presentation today. My name is Pinion Modification and I'm responsible for the customer contact here at FVA. I would like to start my presentation. However, Christine, could you please give me the screen? Okay, while we are waiting for my screen, I would like to say a couple of things regarding our cooperation between FVA and AVL. This year, in the summer, we started a joint cooperation in order to bring you efficient processes over the whole calculation process and the whole design phase. During the design, a couple of calculation stages are present, like the design and the concept analysis, steady state analysis, and modal analysis. However, and then there are also the time analysis, like the dynamic analysis in the frequency domain and the dynamic analysis in the time domain. And it is a bit much for one tool to have all these functionalities. This is why we joined our forces as AVL and FVA in order to have a seamless interface between the tool AVL EXCITE for eAXLE and the FVA-Workbench to transfer the data and make it possible to have a fluent and seamless process. The interface is based on the Reusable Engineering Exchange Standard, short REX, which has been developed by the FVA, so by us, and also Scheffler and SEW. We are working on this interface for a couple of years now. And to my knowledge, this is the first interface to enable programs to interchange data on a standardized model across platforms and across departments. So now we are joining the department of the steady state, the design analysis, and also the calculation specialists who are looking into the frequency and the time analysis, and especially at the vibrations and noise excitation of the gears. And the problem most of the time is if you would like to join tools that you're collaborating with the tool manufacturer, and the tool manufacturer provides an interface to its data. So you can read in or write out the data to the tool. However, the problem is if something changes within the tool that makes it necessary for the tool manufacturer to change its interface, you also have to change the format you write or read. And this reason is that you have high costs and it's very complex. And it also is also prone to errors. With the Reusable Engineering Exchange Standard, we manage to get rid of the complexity and the high costs related to maintaining the different formats and the different in the different tools. However, we have one format to use in AVL EXCITE and the FVA Workbench, and it is also supported by many different other tools and distributors, so that you have one general engineering standard to have a digital and seamless process. I'm very sorry that we still have technical issues with the screen sharing. There seems to be an issue. There we go. Now I'm at the end of my presentation, and I'm very sorry that I have to read it to you. However, I don't want to lose any further time and jump right into the tool. For today, I would like to have a couple of things. I would like to build up a new model with you, export the data into REX, the Reusable Engineering Exchange Standard. Then I would like to hand over to my colleagues, Martin Soppoch and Andreas Süß. They are going to load the model into AVL EXCITE for eAXLE and continue the calculation that we have started in the FVA Workbench. In order to build the model, today I would like to build up a reductor gearbox, like you probably know it from an electric drive. I'm adding a new gear stage, choosing a normal module of 2.25 with a number of teeth of 22 and 65. The helix angle is chosen to be 14 millimeters, and a addendum modification of 2.8. The center distance I'm choosing for 101. The gear width is chosen to be 32 and 30, and the position on the gear is set to 95 and 41. Here in this window, I could also select the material for the gears, and there I'm choosing an AT Chronimo 76, and for the shaft I'm choosing an engineering steel C15. So this is how our model looks, and to make the gears mesh, I'm changing the position of the shaft to -56, and here you could see the gears could mesh. Together with the gears, we are able to also some tools have been implemented into my model, and I'm calling this one, this tool is for the pinion of the input stage, and it has an addendum coefficient of 1.217 and a dedendum coefficient of 1.5. The tip radius, or resulting in the foot root radius, should be fully rounded. Same applies for the wheel of the input stage. There I have an addendum coefficient of 1.1 and the dedendum coefficient of 1.3. it should be fully rounded again. And this enables me now to run my first calculation, a gear geometry calculation. In order to show the results, I'm choosing the gear geometry report template, and I'm selecting the results we've generated. And if we're looking here, right below here, we can see the tooth contact with the generated geometry, and we can see that we have a nice rounded root fillet, and also a good contact ratio, like we can see here in the upper area. So I would like to add a second gear stage. Therefore, I'm clicking on the intermediate shaft, add a second cylindrical gear stage. There I'm choosing normal module of 3, 23 number of teeth, and 61. At helix angle is -12. -12 I'm choosing here because I would like the axial forces on the intermediate shaft to cancel out. As addendum modification, I'm choosing 03. Again, I'm deleting the second addendum modification in order to give a centered distance as a whole number. The face width should be 48 and 46. The U coordinate is again chosen in such a way that it later meshes together with the position of the shafts. Again, I'm choosing the same materials for the gears and for the shaft. As you could see here on the first shaft, the correct material was already selected. Now I could again change the data of our tools, and I'm choosing 1.21 as addendum coefficient for the pinion tool, and 1.3 for the dedendum coefficient. And for the wheel, I'm choosing the addendum coefficient to 1.1 and leave the default of 1.3 for the wheel. Again, here you could see that the position of the gears is slightly off, and this is because I need to change the position of my shaft, and because I need some space here to connect it to our axle. And this is the right time right now to change also the geometry of our shaft. Therefore, I'm defining sections. The sections can be edited in such a table. You could also have a look at the 3D image here, and for every section I add, it adds a new section in the 3D image below. And the last section for the bearing seat with a length of 38 and 50 in diameter. Now I would like to add some bearings. Therefore, I'm adding a component to the shaft. I select the rolling bearing at the position of 57. And here I can already choose a catalog bearing. I would like to select bearings from SKF, and I would like to have a deep groove rolling bearing. And here from the whole list of the possible bearings with that could fit on our shaft with an inner diameter of 60 millimeters, I'm choosing the 6212 SKF Explorer bearing. And I'm also adding a second bearing at the position 237.5. And here I'm selecting another deep groove ball bearing, the 6310 finish. So I have now selected the bearings I would like to have. Last thing to have a look is the actual force absorption. Here, per default, it is given as both direction. However, for this outer bearing, this right-hand side bearing, I'm choosing an axial force absorption to the negative direction, and for the left-hand side bearing, I'm choosing a positive force absorption. This is all related to our coordinate system. You can see it here in the lower left side of our 3D model, and it is referring to the forces of whether it is in positive U direction or in negative U direction. For the intermediate shaft, I would like to load the shaft in from a database. I already saved them in advance. Here you could use standardized parts, and as you can see, the bearings are coming right with the parts, and also doing the same for the input. Now I have to specify the power flow. And as you can see, with the input shaft, it also brought me a force component. So I only have to add a last force component, and I'm selecting it as an output. The last thing to do for me right now is to make sure it fits into our housing, and and there I'm changing the angle of rotation to make it the distance between the input and the output shaft a little bit more narrow, and help the gears to lubricate themselves. You could see they're now right on the same height here, and that helps the whole gearbox in the end to lubricate itself. Now I could add a lubricant to our system, and therefore I'm choosing an ISO VG68 with an oil temperature of 90 degrees Celsius. And if I'm running the system calculation right now, we can see that I'm changing the report template as system report to see the whole results of our calculation. And what I'm expecting to see right now is that we have an unmodified gear, and therefore the load distribution should be rather uneven. And that's what we're seeing right now. Here below the load distribution, I get the modification proposal that hints me to the linear misalignment of the gears that I could input to make it an even load distribution. Same applies for the output stage as well. So this is what I would like to do right now. I add a component to the Pinion modification component, and I select both flanks equal. So now both flanks are getting the same modification to it. However, you could also change it if you want to be precise. This would be the right way to do, and make sure that you apply the loads for the reverse correctly, and therefore you could design the phase modifications with the correct loads and the correct speeds accordingly. As advised, I'm using 12 microns from the beginning of the phase width, and I'm also adding a small lead crowning in order to prevent the edge contact. I'm repeating the same process at the pinion on the intermediate shaft, and here I'm choosing a helix angle modification of 16.5 microns, and again I'm choosing 5 microns for lead crowning. Now we can rerun the calculation, and I would expect to see much better load distributions. You could see that from the first calculation, it changed quite a bit from 1.41 to 1.12. Okay, I could optimize this again, adding another 10 microns. But what I would like to do right now, I could incorporate that into the calculation. I would enable the load distribution calculation in order to also calculate the 3D load distribution and design my profile modification. We could see that in the beginning and the end of the mesh, we have an increased load, line load on the flank. This is fairly normal for an unmodified gear, and we could reduce those load peaks with a tip relief. And if we scroll a little bit down here in the 3D modification proposal, it advises me to add 18 microns as a tip relief. So this is what I'm doing right now. I'm adding a tip relief of 18 microns. Here I could choose the form of the tip relief. I can choose whether I would like to have it linear or circular. Whenever possible, I would recommend to use a circular form. Here on the right-hand side in the help menu, you could see the linear form is ending in a sharp contact area. The circular form starts tangential and has a more smooth effect as a tip relief. I'm also adding a tip relief to the output stage and rerun the calculation. If I would like to see what has changed for my gears, I could select the previous calculation and set it as a reference and compare the reference with my current calculation. And this is generating now a comparison report, and the comparison report shows highlights all the differences in my system. For example, here in the overview calculation, I could already see that I have small difference in the maximum Hertz pressure And if we scroll down to the graph, we could see how it changed exactly. So we could see that the tip relief worked. We have now a smooth end of our mesh in comparison to the previous calculation, and this increases the load here on the beginning of the mesh in comparison to our previous calculation. So by adding a tip relief to my pinion, I also should add a tip relief to the wheel in order to get rid of those load peaks. So therefore, I am adding a component to our wheel where I just add a tip relief of 18 microns with 3 mm of length, and the same process is applied to my output wheel. Both flanks equal, and here I also add the tip relief of 18 microns for 3 millimeters. So now I would be interested in my gear excitation. In the end, I would like to know more about the noise my gearbox is generating, and a first step is to have a look at the static the steady state gear force excitation and the transmission error. We can enable this calculation here in the gear unit calculations tab. There we can see the gear force excitation, and I'm also interested in the bearing life. It's also easy to add. You could add the bearing life, and it's also a good idea to have or to know what the gear load capacity rating says, and I'm also adding this one. I'm starting the system calculation, and here we could see our report. Here on the overview for the local load capacity methods, we could see that the maximum transmission error deviation is about 0.5 or 0.6 microns, which is rather good for a gearbox. However, we could see that the safety factors of our gears are quite slow, quite on the lower side, with 0.77 and 0.79 for both stages. However, if we're now applying a load spectrum, we could increase the safety factors by also adding smaller loads and smaller torques to the mix. For the bearing life, we can see that the extended modified rating life of the SKF catalog shows also rather low life characteristics, especially the deep groove ball bearing on the intermediate shaft is on the small side with 35 hours of rating life. Let's have a look at the transmission error. And here in the transmission error, we could see that especially the looking at the pressure distribution, we could see a sharp load peak here in the beginning of the mesh, and in the transmission arrow we could identify this load peak as well. And if there would be a need to further optimize the transmission arrow by reducing this load peak, we could get rid of the sharp edges in here. In order to optimize this gearbox further, I now need additional calculation methods that, for example, AVL EXCITE for eAXLE could deliver, and therefore I'm exporting the Rex file, and I'm exporting it to my hard drive, and I'm using and then I make sure to click the calculated to add the calculated values, not only the input values. And by this, we could also transfer the gear, the bearing geometry to AVL EXCITE. With clicking OK, I have exported Rex successfully, and let's see what we could do with it in AVL EXCITE.
Okay, let me share my screen. This is the other one, I think. This one. Yeah. I hope you can see my screen now. So this is EXCITE for eAXLE. As first step, now we will import the Rex file. So thank you, Benjamin, for the file. For this purpose, we click on Import Rex Model. We point to the location where it's stored. Now let's open the model. This takes a few seconds. Here you can see now the Rex import log. Now let's search if there were any warnings, for example. So these are the warnings. Basically, I cannot see any critical warnings, just the warnings. These warnings are caused by our limitations of our shaft modeler. Our shaft modeler is not as sophisticated as the shaft modeler in the FVA-Workbench, but they will not. They will be solved automatically. Now we can close the Rex import log. Now you can see here the model already. Now, before we start the simulation and so on, we will just shortly check the model. First of all, we will visually check it, so you can see that all the bearings are in place. We have all we have both gear stages in place. We have the loads. Now the second step is now let's check the boundary conditions. So let's check the loads. On the input, we have 300 Newton meters, which is correct. Also, the direction is fine. Then let's check the output. Is 2,350, which is also correct. Perfect. Now what we have to do is to check the speeds. For that purpose, we will check this shaft, this input shaft. It has also the correct speed. This means we have more or less a correct model. The next step would be now to prepare the model for the simulation. For this purpose, we have to select in the eAXLE reference body, which is in our case the input shaft, and we have to set some solver settings. We will use the solution reference angle because we want to simulate 4 revolutions of the reference body. The other values we don't have to touch. Before we jump over to the simulation, we will now shortly check the kinematic animation. So the kinematic animation is purely considering kinematic relations between the gears and the degrees of freedoms of the body. And if this kinematic animation works fine, this is always a good indicator that the model is correctly created. So you can see that the gears and the gear shafts are properly rotating, and more importantly, none of the bodies is flying away, which is always a good indicator. Okay, the next step would be now so currently we have purely rigid bodies. We don't have any external FE measures taken into account or used. Therefore, we will simply use this rigid model now and run the simulation in order to check if the current model is really perfectly prepared for the simulation. This we now can skip basically because I prepared this already before this presentation. Now we can directly switch to the results. Here you can see the model in the result. We will now just shortly check the 3D animation, but in this case now the 3D animation is considering the entire simulation, so really the full dynamic of the system, including forces, loads, and deflections of the bodies. So let's start the animation. So here you can see some forces, the forces of the roller bearings, of all the individual elements. You can see the contact forces on the gears. So now we can already check if the applied modifications are properly set. So it looks fine. The force distribution looks properly here. So thank you, Benjamin, for this. Also on the other gear stage. So this looks great. This means we can basically now continue with a flexible bodies. For this purpose, we have to, for each body, we have to select, instead of our internal rigid modeler, we have to use an external condensed file. In this case, it's the housing. Now let's use also some 3D mesh so that we can see some surface. So here you can see how the housing looks like. It is a gearbox mounted to a test rig, basically. Now let's have a look inside. So, because we have to check if all gears and on the positions of the shafts and the bearings are correct. So this seems to be the case. We can have a look maybe deeper inside so we can check the bearings. So it looks fine. So what's the origin of this EXP file? Typically, we use our internal EXCITE component modeler tool. This component modeler tool offers certain tasks and for related to CAD and FE, to the FE world. And we would simply use now the task for condensation, the condensation task. What does this mean? This means that the condensation, the component modeler, is taking the geometry from the EXCITE body. So all the positions of the gears, the bearings, and so on, and together with the FE mesh, and then automatically generates the retained nodes for the joints and for the forces, together with the required multi-point constraints. And then you send this data to the condensation, which is creating a so-called EXCITE body file, short EXP file. And this file can then be used directly at the bodies. So the next step would be now to switch over to flexible bodies for flexible files for all bodies. This we can again skip now. So here you can see the already fully prepared model. You can see the housing, but also all three shafts. I have shortly to mention that this differential is modeled as one body. The reason is simply simplicity for this presentation. In principle, you could model the entire differential as individual bodies in the FVA-Workbench, but also in EXCITE for eAXLE. This would be possible if you go for that solution. Okay, we have again the fully prepared model. Now, once again, we can check the kinematic animation, just in case so we can see the 3D meshes are rotating and the gears are properly in contact, so everything looks fine. Now let's switch over do the results. So again, I did the simulation already before this meeting. Here you can see now the model in 3D. The difference is now that we really have 3D measures and flexible bodies in place. Now let's hide just for now the casing and the intermediate shaft. Now you will see the difference between rigid bodies and flexible bodies. So you can see there is much more dynamic in the system. Now let's check again the distribution of the forces. So you can see typically it's properly distributed, but if you look at the beginning, for example, then you will see there are some impacts. And these impacts are causing or exciting the entire model. Or bodies are flexible. This means they are really excited in their motion. And this will again impact the force distribution in the gears, for example. And you also can see the forces on the bearings. So they are way higher now than before. So let's run the simulation a bit and let's have a look on the results. So you can see really there is some kind of vibration in the system, which has much more influence than simply the compliance of the bodies. So now let's investigate what exactly is causing these vibrations in the system. For this purpose, we will have first of all a look on the housing. So now I will deactivate this clipping plane, and now we can switch. We have to activate the deflection for the housing. Therefore, I will set a proper deformation scale, which is 100 in this case. And now we can let's go back to 0 degrees. And now let's run the animation. So now you can see really heavy vibration of the entire gearbox. And you also can see that here the gearbox is really inclined, which will automatically then tilt the shaft inside, which has a significant impact on the force distribution of this gear stage in between. Let me shortly explain in what's the reason for this impact. The reason for the impact in this model is simply that we start a simulation from 0. And at the beginning of the simulation, you have typically backlash in your system. This means you have backlash between the diff, you have backlash between the rolling elements and the inner outer race, and the elements in the diff have simply to travel through this backlash, and after they get in contact with the other tooth, basically this will cause this impact and the vibration and the excitement of the system. Finally, we can also have a look on the differential. So how is the differential behaving? So again, we have to activate the deformation, displacement, and scale it to 100. Let's have a look on it from the beginning again. Make it a bit bigger. So you can see there's really a heavy vibration going on in the differential. So probably the design of the differential is not rigid enough. It seems to be too weak, and it's not also tilting. You also can see the gear. The shape of the gear is significantly changing. And this, on the other side, if you now have a look on the force distribution, is exactly causing this force distribution. Sorry. To rotate the gear, that you can see properly. The shape is really wild, I would say, and then this is causing this edge loading case of the gear. Yeah, that's it so far from my side. I will hand over now to Sopuch Martin. He will show you some additional results. Thank you.
Yes, thank you very much to my predecessors. This was a very impressive presentation, I have to say, on both sides, on the FVA workbench, but also to see how smoothly actually the models can be transferred to the EXCITE eAXLE. I hope you can already see my presentation, seems to be the case. I just want to close now our presentation about the combination of the FVA workbench and EXCITE, and I want to give you an additional idea about typical results which you can get in addition out of an EXCITE simulation. We are focusing in this kind of application mainly on the dynamics and the NVH behavior. You have already seen in the presentation of Andreas Süß that there is a lot of interaction basically between the system dynamics of the shafts and also of the housing to the gear contact. And this is typically something which we look at the beginning. This is about the dynamic transmission error. So we are checking out what is going on in the gear stages, in the different individual gear stages. And we very often see that the dynamic transmission error, which really occurs under the dynamic influence or the total influence of the inertia, the flexibility of the system, can be quite different as this comes out from the pure static simulation or static calculation. Again, here you can see a situation, and I hope I can start here the animation. Seems not to work properly. Okay, again. Today we have not a good day. I'm not sure, can you see something on your side? No, obviously not. Nevertheless, there is quite some interaction between the movement of this differential shaft with the gear contact, in the very same way as before Andreas was presenting. And this already gives you an idea that there is quite some modulation between the system dynamics and the actual transmission error. The second part we typically have a look on is the dynamic component loads. It is also very obvious that the internal dynamics of the gears, but also the whole system dynamics, is leading to quite some amplification in the component loads. And this is, of course, also a very crucial point for the dimensioning and layouting and finally the lifetime calculation of the components, because due to the dynamics in the system, you get amplification above the pure static value. And as a consequence, you can make yourself here an idea and an impression how much the dynamic is really increasing your forces, and probably it is necessary to adapt in the design process your factors regarding internal gear dynamics or even the application factor. The third thing, or the third point, the key issue which we are looking here, is structure-borne noise assessment. EXCITE gives us actually a very nice possibility to have a look at the whole acoustic transfer path. That means starting from the excitation, from the gears, from the roller bearings, later on probably also from the e-machine, throughout the individual components, and also throughout the flexible structures we have in the simulation. And one of the most important structures or components is, of course, the housing, because the housing, and especially the housing vibrations, are finally causing the noise radiation from the transmission to the outside. So unfortunately, again, here the animation is not working in the screen sharing, but nevertheless, I think you saw before very nicely how our structures and our housings move under the dynamic conditions. And at the very end, we also have a possibility in EXCITE to move from the vibrating structure of the housing to the real airborne noise. So it is possible also to predict, for instance, the sound pressure which is generated in the neighborhood of such a reference sphere, and we can really predict what the human's ear is basically hearing in terms of noise excitation. And I have brought here some kind of sound sample, but I'm not sure if it really works. This sound sample is actually a simulated noise. So we are taking basically the simulated sound pressure, and we are creating or actually doing a synthesis of the vibration of the sound and putting this into a kind of waveform file. Probably it works. Let me just try if we hear something. Obviously not. Okay, doesn't matter. But just to give you the idea, okay, we can even create a sound, an audible sound from the simulation. Good. Moving on actually already to the closing of our presentation. I have here a summary of the basically benefits and of the value which you can create when you combine the both softwares, namely the FVA Workbench and the EXCITE for eAXLE, by the very nice interfacing through the racks. And if we put a focus on the workbench, so if we look at the workbench, there is clearly the strength of the workbench that we have a very nice coverage of the whole concept and the design analysis. So you can basically do the system sizing, the component sizing, but also the fundamental lifetime prediction very nicely and easily in the workbench. Benjamin has already shown this before. You get very good reports, very nice reports. You can very easily do your static load calculation. You can really nicely optimize already, and this is a point I want to emphasize here, you can very nicely optimize your gear microgeometry as outlined by Benjamin under static conditions, and this is a really good starting point for a subsequent dynamic analysis. And what was not shown today, but what is also present in the workbench, of course, is the basic power loss calculation. So you can get already on the level of the static load distributions a very detailed idea about the power loss in general and power loss distribution. Coming to EXCITE for eAXLE, it becomes apparent that if you use the REX interface, for instance, from the workbench as an exported model, you can have a very easy entry to the world of the flexible multi-body dynamic simulation. And we are actually offering this in both in time, which is our standard solver, and this was also part of the presentation of Andreas, but we are also offering in the future frequency domain solution. So it will be, or it is, and it will be in the future, very easy going in order to create a flexible model for the multi-body dynamic simulation. And by that, of course, you are opening up the whole world of the dynamics and the whole world of the vibration and noise assessment, as I have outlined in my result overview. Moreover, and this is something which we didn't touch today, but all of you know, especially when we move into the automotive area, we have to deal also with electric drive units, which means that we have a very tight combination of the gearbox and the electric motor. And as soon as we have to deal with such kind of system, it's not only the gear excitation or the roller bearing excitation, there is also electromagnetic excitation and torque ripple entering the stage. And we have here in our AVL simulation suite a very nice tool, which is the electric motor tool. And with this tool, you can calculate basically your electric excitations in terms of torque ripple and stator excitation. Completely different topic, beyond the mechanics, it is possible to export geometry and motion data from EXCITE, and you can feed this data into CFD tools. We as AVL have two major, or actually we have one major CFD tool here in place, which is the FVA-M. And FVA-M is actually a traditional CFD method, but it employs a very progressive method called embedded body. And with this method, you can very easily process the geometry and the motion data in order to calculate the oil distribution. I will not go in detail to this, but you can very nicely see which of the components, the gears, the rolling element bearings are getting really oil, and you can investigate different oil levels, different positions of your elements and so on. So this is really a nice tool to get a good idea about the lubrication system. We are also offering, beside the classically finite volume CFD, one tool which is called Pinion Lab, which is part of the AVL group. And this is a particle-based CFD. It is not, in terms of physical resolution of the problems, it is probably not that capable, but it is still very fast and can do a lot of things. Finally, I want to emphasize the real benefit of the tool combination is that the combination of both of the softwares can cover basically all the tasks which are relevant for the entire development process of the transmission or the gearbox. And finally, I want to here conclude and say thanks for the participation and your kind attention. We have here at the end the link to our social media channels, which I just want to motivate you and visit or motivate you to visit. There is on the one side the channels from the FVA Service GmbH, and on the other side there are the known channels from the AVL. And with that, I end our presentation, and we are basically open for questions. Thank you very much.
We already have two questions. The first question is, which versions of REX are supported? Since last Friday, the REX 1.4 is released, and however, for this common interface between AVL EXCITE for eAXLE and the FVA-Workbench, it was more sufficient to, or it was sufficient to go for 1.3, version 1.3. However, if there are benefits in the newer versions of REX, there might be the possibility to upgrade that as well. Second question is regarding the information of the lubricant. At the moment, the lubricants in the FVA-Workbench are parametric. Is a parametric design. We're looking at densities and lubricant types and viscosities, and the same is true for the data in REX. At the moment, we transfer the density at 15 degrees Celsius, the lubricant type, the name of the lubricant, and the viscosity at 100 degrees Celsius, and the viscosity at 40 degrees Celsius. Are there further questions from your side?
There is one question on my side. The question is, how long does the AVL simulation take, for example, to simulate a run-up from 0 to 7,000 RPMs? I can tell you that, for example, this model I used in the presentation took for 4 revolutions 1 minute, so pretty fast, I would say. I mean, it clearly depends on the complexity of your model. Do you have 2 stages? Do you have 10 stages, gear stages in place? And so it really depends on the physical representation of your model. But maybe Martin Soboch has some experience.
Yeah, I can definitely state to this. As Andreas said, it vitally depends on the complexity of the model. And of course, our experience is that under real tough project conditions, so if you have a large condensed structure for the housing and basically you have all the bodies in place in form of a flexible representation, for such kind of run-up, you can take about 5 to 6 hours, I would say. But it depends, of course, how fast you do that run-up. I assume here we are speaking, if we want to go from 0 to 30,000, we are speaking about 20-30 seconds. So this is already very long for a time to main solution, and this will of course take some time. On the other side, if you are unsatisfied with this kind of calculation time, and if you say, okay, I'm more looking into stationary conditions, you are free to use our future frequency domain solution. And with the frequency domain solution, you can get this result in a fraction of time. So if you're talking about calculation time, it's also always very crucial to differentiate between the transient calculation, which is time domain, and a frequency domain solution. And of course, out of a transient calculation, you get much more value and also result, basically, content of results.
There's a second question on my side. Can I define a viscous damping in the flexible bodies in AVL EXCITE? So this is now possible with the next version, as far as I know. So the answer is simply yes.
I have one more question here. are there any other evaluation parameters for the tooth mesh available, like engagement stiffness, curves, C gamma, tooth force level, and excitation level? For the gear force excitation, we are relying on the FVA research project 338. And in this research project, not only the transmission error was developed, but also the gear force level and the excitation level as a measure for audible noise within the gear mesh. Of course, you could also export the stiffness of the gear and the stiffness of the gear mesh and display it in our reporting system as a C gamma, or there are also possibilities to calculate the dynamic mesh stiffness within the FVA workbench. Okay, do you have more questions? If not, we are 2 minutes. Yeah.
There's one question on my side. Are these parameters also in eAXLE available? Thanks. I'm not sure which parameters are meant here. So in general, in eAXLE, sorry? So in general, in eAXLE, you are able to use parameters, and if so, that's about eAXLE, and the general geometry parameters are overtaken from the workbench, for example.
Okay, we are already 3 minutes over time. I'm very happy that you took the time to have a look at our solution today. If you have further questions, please contact us over, for example, FVA-Service.de. There you could contact us via the information mail, the info@FVA-Service.de. And if you have questions to Martin and Andreas, you could also, I suppose, use the known contacts on the homepage, or you probably already have the contact information to them. I would like to thank you for your time and for your interest, and would be happy to hear from you soon. Have a nice day. Bye-bye.